Good evening, everybody. Am I audible?
Yeah, you're audible, Ram.
Yeah, okay, fine. So how is everybody doing? Just wave your hands, type in chat box. So nobody is fine except Himanshu. Is it so?
Guys,
Guys,
we need your response, guys. It will be a very interactive session if you are involved. So kindly respond, at least raise your hands, or at least type chat, good evening, something. Come on,
yeah,
guys.
cool, Sherlin. Okay, what were the insights from yesterday's session for you all? Cool, I can see people raising hands. Yeah,
Yeah, guys, that's the spirit. Good.
cool. This is what we expect. So, guys, how was your quiz yesterday? And did you find anything to be improved from our side or something? Do you want to say? You are free to speak. Yes, Avantika, you want to speak anything or you have raised hand? I can see. All right. Okay, then, or you guys have any doubts from previous sessions, or you guys need any assistance from our side? Okay, then, yeah, if everything is clear and then yeah, we are good to go and we are ready to dive into today's session. I'm myself NT Dheeraj and I am pursuing currently third year CSA in Sastra University. Today, myself uh, and my friends Manindra and Tarun Vaibhav are going to present you the session Sensing and Perception. So, guys, have you ever wondered how a robot thing? I mean, how does it know what it has to do? For example, you see, we'll take yesterday's example itself. If you are touching a hot pan, you are retracing your hand back, or you are pulling your hand back. Uh, can anybody tell the analogy related to with these robotics terms, sensing and perception? Can anybody give analogy or some kind of inputs from their side regarding this? We'll be glad to hear any kind of input. There's nothing wrong and right. You can type in chat or you can unmute and speak. Okay, at least tell me what is the perception in your view?
Guys, you're free to chat. Nobody's gonna tell anything to you guys here. Type whatever the answer you have in your mind.
You
Nothing
all
is
are students, guys. We are not any professors.
Yeah, even we are students like you. That's it. Come on, guys. Completely free. Feel open. Type whatever you feel in the chat.
Don't
Whatever the
worry if
answer related.
yeah, don't worry if you type in some spelling mistakes. We are humans. Yeah, the question is I had two questions, in fact, meanwhile, because none of you was speaking. The questions were, can anybody tell some analogy for these terms that you are seeing on screen, sensing and perception, analogy to human? Or can you give some inputs regarding sensing and perception? Anything? Yeah, Himanshu, touch, nerve cells, and yeah, okay, message to brain cell, brain respond. Okay, you're giving the entire process. Okay, and then after feeling hot, what is the? I mean, I think that's incomplete. But yeah, you have given almost 70% of the process. Sensing, feel, and perception, thinking or views, right? Sherlin is almost near to the right answer. Cool. I'm glad to see inputs from you guys. Okay, so let's take yesterday's example itself. The if when you touch a hot frying pan, your hand has your skin covers it, right? So skin is a sensory sensing thing. So this sends signals to your brains that the body is touching something which is very hot and which may burn the skin, and the brain has something which is analogical. This is which is an analogy to the microprocessors and microcontrollers which you saw yesterday. This thing present on board in terms of electrical terminology, I'm speaking, that makes these signals which were sent by sensors are processed, and they are processed into something which makes sense, and that piece of information is termed as perception. And with this perception, the microprocessor or microcontroller will direct the actuators in the sense, like if you take your hand, the end effect, taking back your hand, so the folding of hand can be termed as an actuation process in robotics. So to explore all this, we'll start with today's session. My friend Tarun Ramavaibhav will take over this session. Thank you.
Yeah, Dheeraj, thank you. So, hi guys, this is Vaibhav from CSC Core Department. Currently completed my second year and going in the third year. So, yeah, I hope your sessions till now are wonderful and you're learning a lot new things. Now today we are going to discuss about like sensing and perception, whatever the introduction that Dheeraj has given you. The same thing. Let's like what we thought of, like directly going into the concept of sensing and perception with robotics. We wanted you people to involve to understand the basic meaning of sensing and perception in humans' perspective. Then we'll go directly into robotics. So yeah, we have different sense organs, right? What we wanted to convey is like we have different sense organs. As a human, we have eyes, nose, tongue, ears, skin, etc. So these are the 5 main sense organs of our body. So these sense organs will help us to observe any changes that occurs around us. Like if suppose someone in your house switches on a TV and there's change in a channel, you notice a change, that a channel is changed. So how you're noticing it? With the help of your eyes. Or if I'm speaking right now, you're able to notice a change that some audio is coming out from this meet. So your ears are able to detect that change in the actual environment. Like suppose if I stop speaking, the meet is completely silent. But now when I start speaking again, you can recognize that someone is speaking. You can able to hear something audio from the meet, which means like there's a change in your environment. The environment is like, suppose the meeting is an environment. So if I stop speaking, your meet is silent. If I start speaking, there is a change in the environment of the meet that someone is speaking out, which means your ears, which is a sense organ, it's able to detect some change in the environment, and it's making you alert. You're becoming alert that someone is speaking in the meet. So yeah, what's that? What is that? So we'll be listening. So that's the basic idea of sensing and perception, guys. Nothing else than that. See, as simple as it is. Sensing means we are surrounded by an environment. What are the things around us? They are completely environment around us. So environment is continuously changing. So changes will happen continuously in the environment. So when you are able to identify or observe the changes or feel the changes that occur in your environment, because that's nothing but sensing. And perception in the sense how you're going to react to that change in the environment around you. So that's simply called as perception. If suppose the same example as we discussed recently, very recently in the meet, so you are touching some very hot thing. So your skin senses that you're touching something very hot. So then what's your immediate reaction? You try to pull your hand away from the that hot material so that you could save yourself, which you feel that it's uncomfortable for you. Your skin senses that it's so hot and uncomfortable for you, so you pull your hand back. So that's perception. That's how you're perceiving it. So yeah, responding to it. How you're going to respond? Different people will have different response to different actions around you, right? So how you are going to respond to this particular situation or to the change that happens in your environment around you. So that's basically perception. So that's the basic idea of sensing and perception. So I hope everyone is clear with this basic idea of sensing and perception in humans perspective. Don't go into robotics perspective, guys. As of now, as of thinking of a human's perspective, that is sensing and perception, right? Understood? Got it right? Guys, come on, respond in the chat, guys. Sensing and perception, the basic difference. Yeah, good. I hope everybody understood it. So that's the basic difference, guys. Nothing else than that. So right, coming to robotics, moving into the topics of robots. Let's see. So sensing and perception. So yeah, when can you say a robot is an intelligent robot, guys? Suppose you have a robot. So what works you expect your robot to do for you? Attending the meet instead of you, that's a great idea. Someone can suggest. Actually, this question was asked to us when we were in your place. Someone from our batch has also answered the same question. Attending meet, like if I have a robot with me, I'll ask my robot to attend the meet instead of me. So how many of you think that same? When can you say a robot is intelligent, guys? Come on. Any ideas? Yeah, it can take decisions automatically, perform tasks and respond to the situations wisely. Yeah, take care of home when we are not there. Okay, that's not a bad option. Yeah, guys. So this is what I want. Yeah. So when can you say robot is actually intelligent in the sense when it can take its own decisions, when it can identify the changes in its environment, like sensing, and it can react to those changes in the environment, like perception, as of humans. So sensing and perception are the basic things that a human can do. So if the robot also can do the same work like sensing and perception, if a robot can identify the changes in its environment, and if it can react to those changes in the environment immediately, like taking some action, a robot taking an action, so then you can say that a robot is useful. We can't simply have a robot with you and it's simply sitting not doing any work, right? It's not good. We expect something high from a robot, right? We want our work to be easier. We want our robot to be responsive, sensitive to the changes around it, and responsive to the changes, quick response to the changes around it, like perception. That's what the same concept moving into the robotics also. Sensing means a robot, if it is able to sense or identify or observe the changes happening in its environment, if it is able to feel or identify the changes happening in its environment, that's sensing of a robot. And perception means you will be programming a robot, right? So when to react in which way for which situations. So if it senses that situation around it and it reacts to the situation, reaction in the sense not some correct sort of reactions, like respective reactions, not irregular reactions. A change in the environment has happened, so you need the robot to respond correctly, which will solve that problem, or which will solve that problem causing the change in the environment. You need your robot to be responsive and correct to that sensing. So that's perception. Sense, it senses the changes around it. Perceive, it will perceive the sense, and then it will be able to react. Then that's what sensing and perception in case of robotics. Then you can say that a robot is intelligent. So if you go to high levels of intelligence of robots, you have artificial intelligence, neural networks, deep learning, and all those. But we are speaking about basic intelligence of a robot. When it can sense and perceive, we can say that a robot is an intelligent robot. It is okay. It's a first to mediate level of intelligence, right? So right, what is a sensor? As of now, we spoke about sensing and perception. Now, what is a sensor? when you guys understood sensing and perception, its sensor is nothing but, you can simply say that it's a device which is used in robots to help robots to identify or sense some changes around it, right? It's nothing but a sensor. Like you can derive your own definition of sensor as well, as guys. I mean, like apart from the textbook definition, if you could understand the basic information about sensing and perception, if you have a basic correct idea of sensing and perception, a sensor is nothing but a device used in robots to help robots to sense the changes around it. That's nothing but a sensor. So yeah, it's already written in the slide. Sensors are devices that detect and respond to the changes in the environment, able to identify or able to detect the changes happening in the environment. That's nothing but a sensor. So what is the basic work of a sensor? The basic work of a sensor is to sense the changes in the environment. So it converts a physical phenomena into a measurable analog voltage, converted into a human readable display, or transmit for reading or further processing. Yeah. So once a sensor senses something, you need the sensor to perceive the sense, and then you need that sensor to react according to that change in the environment, right? So we need the sensor, we need the robot to react. That reaction will be identified by humans, right? So humans should understand its reaction. Humans should understand its reaction, how it is reacting, why it is reacting. Is that reaction appropriate or not for that particular change, right? So it should be converted into a human readable display or human understandable display, in other words, right? That's nothing but a simple sensor. It will sense the changes in the environment and then convert the physical phenomena into some analog voltages so that human can understand that particular reaction, and he can come to one conclusion whether if the reaction is correct or not in that way, in that sense. So it's a sensor, right? Next, perception. Perception we have already discussed. It's nothing but how you're going to perceive the sense and how you're going to react to that sense. That's nothing but sense, perception. So making sense of unstructured real world, and yes, to make sense it needs some data. So whatever the changes in the environment, that is taken by the robot, right? So in robot perspective, those changes in the environment which the robot will take, they are inputs to the robot, right? That's why we mention here which is the input given by the sensors associated with the robot. So in talking in terms of computer technology, or talking in terms of technology or robots perspective, whatever the changes occurring in its environment, that will be identified or detected by the robot, and those changes are actually the inputs taken by the robot. And for those inputs, it will take the inputs, process the inputs. That is nothing but perceiving the inputs, and then it will do the process of perception, and it will react to the particular change. So that's perception. So here two types of basic perceptions, like action oriented perception and then active perception. So perceptual processing tuned to meet motor activity needs. So there is every robot will be having motors, right? So motor activity needs are met by that perception device or something, though it is an active oriented perception. Action oriented perception. And an active perception means agent can use motor control to enhance perceptual processing via sensor positioning. So changing the position of sensors and enhancing perceptual processing. Like you can change the position of sensors and then you can identify different changes in the environment and then enhance your perceptual processing, and then you can give a more appropriate reaction to your changes in the environment. That's an active perception. Like you not only depend on one position of a sensor, your sensor keeps continuously changing its position, identify various changes around its environment, take all the inputs, process all the inputs, perceive all the inputs, and then give you an appropriate reaction. That's an active sensor. So since we have discussed sensing, perception, sensors, everything till now, what's the difference between sensing and perception? So as of now, it should be clear to you all that sensing and perception, nothing big difference. The only difference between sensing and perception, sensing is nothing but detecting the changes in its environment around it. Perception is nothing but taking what are the changes that you have sensed, taking that sense, accepting those inputs, and then processing them. In other words, in technical words, you can say you are perceiving the inputs or you're perceiving changes in the environment, and then you're going to react. That is perception. What way you're going to react. That is perception. That's it. And nothing much big difference between sensing and perception other than that. While the second point tells that sensing needs a device called sensor. Yeah, we have discussed it earlier. What is a sensor? A sensor is a basic electronic device used in building robots. Basic robots also will have different types of sensors, guys. So a sensor is a device which is used in building robots to help the robots sense the changes in its environment. That's a sensor. So sensing needs a device called sensor, whereas for perception, signals from sensors have to be transformed to other form. We have discussed earlier here, guys. It converts the physical phenomena into measurable analog voltage, and what are the changes it identifies in its surroundings. it has to perceive the data, and then it has to react appropriate to that particular changes, right? So sensors have to be transformed. What are the signals the sensors will be taking? Those have to be transformed to other form of signals which can be interpreted. Therefore, it needs a transducer. Sensor also needs a transducer in between. Why? Perception also needs a transducer there, because you're perceiving the inputs, right? So if you perceive the inputs, you need to process those inputs, and then you need to give an appropriate reaction to those inputs. So you'll be needing a transducer. A transducer is nothing but it's simply like helps you in perceiving the data, interpreting the data, and then helps you in giving you an appropriate reaction to the change occurring in the environment. That's it. So yeah, the guys, I have a basic question to you. So if you see here, this is a sensing model which you can see on the screen. So yeah, you will be having an environment, and a change will occur in the environment. That change in the environment is identified by the sensor. So that's the flow of the diagram. But finally, the robot action is also going into the environment itself. So does anybody have a logical reason why it is so? Why the sensing model is so like environment is the main cause of sense, and then the robot action is also going back to the environment. The direction flow is also going back to the environment. So can anyone have the basic idea of why the model is designed in this way? Guys, any idea of why this environment to again environment? It starts from environment and ends with environment. So why it starts with environment? Why a sensing model starts with environment and ends with an environment? So any idea, guys? A basic logic. Yeah, that's the correct answer, guys. Environment also changes according to the robot's action. That's the correct answer. That's why you can see in the diagram in the model that environment is there. You will be having a change in the environment. That change in the environment is identified by the sensor. The sensor will sense the changes in the environment. It will be converting into an observation or an image. So it will sense the changes. So if you are a human, you can directly observe with your eyes, and then hear with your ears, sense with your nose, taste with your tongue, and etc. But for a robot, whatever the inputs, like all these changes in the environment are sensed by sensors in the robots, and those are taken as inputs data, right? We have discussed earlier. Those are inputs to the robot to process further processing. So those inputs are either observations in form of raw data inputs, or either they are image form inputs. So those will be perceived. This perceptual schema, percept, modal schema, all these are like perceiving parts of perception where the input data is perceived, and then final appropriate robot action will be taken, and same robot action will cause a change in the environment again. That's the basic idea, guys. That's why your sensing model starts with environment and then ends with an environment again, right? So basic example, you're sitting inside a chilled room where your AC is on for more than 1 hour, suppose. So you feel it too cold. So what you do, you feel it too cold. So you're sensing that your environment is too cool. So you try to switch off the AC. When you switch off the AC, but your room is completely closed, slowly the room temperature starts to increase. Suppose when your AC is on, your room temperature is 16. But when your AC is off, like when you switch off the AC, your room temperature starts to increase from 16 to some 20, 22 or something, right? So what you have done here is you are sitting inside the room. You sense that your room is too cool. So you took an action. You sensed it. You perceive the data. Your brain perceived the data. Your brain perceived the sensing, and your reaction is to immediately switch off the AC. When you switch off the AC, the room temperature gradually starts to increase from 16 to some 20, 22. Later on, it goes on increasing until and unless you provide some ventilation in the room, or you again on the AC, which means your environment temperature starts to decrease when you are on AC, which means that there is a change in the environment. And when you sensed it is too cool, you switched off the AC. Again, there's a change in the environment. Your perception, your reaction, your action caused a change in the environment. Then again, the temperature of the room started to increase from 16 to some 20, 22, and so on. Again, there's a change in the environment. So likewise, an environment change will cause the sensor to get activated. It will be sensing some changes. It will take the observations or images. It will perceive the data. An appropriate action is taken, and again that action will cause a change in the environment again. That's the reason why the sensing model starts with an environment, and again you come back to the environment again. So this is the basic sensing model. I hope everyone is clear, guys. Clear with the sensing model, right guys? Sensing model. Yeah, fine.
Bro,
Thanks. Yeah, bro.
I have something to ask, bro.
Yeah.
The sensor sense what's happening in the environment and send signal so that it helps robot to react, no?
Yeah.
According to yeah, bro. I have a little bit doubt in that. Thank you.
No, you want me to explain it again?
No, bro.
No, I didn't get your point. Sorry.
No, bro. In the sensor, the sensor sense what's happening in the environment, right?
Yeah, it will detect the change happening in the environment. Yeah.
And perception means it helps robot to think what to do, no, according to the environment.
It will perceive. It will take the inputs. It will process the inputs. Like perception in the sense how, like in what way you're going to react to that particular change in the environment, to the particular sense.
Okay.
Yeah, clear?
Yeah.
Yeah, fine. Thank you.
Excuse me, Tarun.
Yeah.
Why don't you explain the same with the same analogy that you have been using? When you touch a hot pan, what is sensing and what is perception?
Okay. Like when you touch a hot pan, you feel it hot, right? So that's sensing. Your skin senses that the temperature of the pan is too hot to. It makes you uncomfortable. So you're sensing the heat of the pan. So you perceive that, like, your brain perceives that it's too hot for you, so you cannot bear it. So you immediately react. So after this perception, the immediate follow-up is your reaction. You remove the hand away from the pan. If that's the case of sensing. Sensing is where you where your brain identifies that the temperature of the pan is too high to bear, unable to bear for you. So your brain immediately perceives that sense. It will take that sense, and then the immediate reaction sent by the brain is like you have to remove your hand away from the away from the pan. So this gap between this action and then reaction, right? That's perception. Action, there is a sensing. For that particular sensing, you have an appropriate action taking place. So which decides this appropriate action is like in between this process of perception happens, where you take the inputs, where you process it, and then appropriate action is taken out. Is it clear, Anna? Like, is it enough?
Yeah, why don't the attendees answer it?
Yeah, guys, clear? Like the basic, like the difference between sensing and perception. There is a sense, there is an action. So the sense and then action process happening in between these two phases is like perception. Yeah, fine. Thank you.
Tarun, are you speaking?
Tarun, you are on mute.
Okay, thank you. Yeah, physical attributes of a sensor. The first one is like field of view. So first one is like field of view. What is this field of view? So whenever you're designing a sensor, you have to follow all these basic physical attributes so that your sensor will be, appropriate sensor. So first one is like field of view. So what do you understand with the term field of view? So field of view means when you take a sensor, at one go, a sensor can, it can detect or it can identify the changes in its environment until some range. So if you want to identify the changes happening in the environment beyond the range, you need to change the position of the sensor so that that particular area comes into its range, or that particular area comes into its field of view. So whenever you're designing a sensor, a basic sensor, you need to first determine the field of view of sensor, right? So that's the first thing you have to keep it in mind. Second thing is like range. What is a range? A range is nothing but difference between the maximum and minimum value of input that can be measured, right? So a sensor will be there. A sensor will, what a sensor does, a sensor will sense the changes happening in the environment, right? So it will be taking those changes in the environments are taken as inputs. So that input will be having either a maximum range or a minimum value to be sensed, right? So that particular difference between the maximum value to be sensed, that can be sensed, and to the minimum value that can be sensed, that difference is nothing but range. So you have to even determine the range of your sensor whenever you're designing a sensor, right? So the basic physical attributes of a sensor, guys. So field of view is a basic physical attribute of a sensor. Range, you have to determine the range of a sensor. Like what is the upper limit of the sensor? Like what is the upper limit, how much it can detect? What is the lower limit, how much it can detect? So the difference between the upper limit and lower limit is nothing but the call as range. So that's the range. Next, responsiveness in the target domain. So yeah, responsiveness is nothing but changes, like its reaction to the change happening in its environment. So the basic thing what we expect from our technology nowadays is immediate reaction. We need everything to be fast, right? Starting from our networks like phone, web services, web browsers, like Google search, and everything we need to happen in a jiffy of seconds, right? The same applies to the robots also. You need your robot. You can say your robot is more effective and more efficient and more sensitive to its environment if its response is in a minimum amount of time. So response in the target domain, you need to set the response time of a sensor. That's also a main attribute to be considered when you're designing a sensor, guys. So you need to set your sensor's response time. So the minimum your response time of a sensor, the more active it is towards its changes in the environment. That's the third property. Then accuracy. How much accurately your sensor is able to detect the changes happening in the environment. That's nothing but accuracy. That means, what do I mean by how much accurately detecting? I mean that deviation from the exact quantity. There is a change in the environment. So that particular change will be having some exact value. So the deviation, what is the exact value of change happening in the environment, and how much up to maximum extent your sensor is able to detect. That's nothing but accuracy. Like how much appropriately you can say, or in other words, you can say how much minimum amount of deviation you're having from the exact value to the detected value by the sensor. That's accuracy. So the lesser the deviation you have, the more accurately your sensor is, sensing the changes in its environment. So that's the fourth property. Then repeatability. Repeatability, the word itself, the attribute itself has the name called repeat. Repeat in the sense sensing, like identifying the same environment again and again, right? Suppose you have an environment in you're sitting in front of the laptop now and you are attending this session. Now this particular moment of time, I'm speaking about physical attributes of sensor. But before 5 to 10 minutes, I was speaking about sensing and perception, right? So the situation is same. You're sitting in front of your laptop, you're in the same meeting, but there is a change in the there's a change in the topic of what we are discussing as of now, as of present. So before we were discussing about sensing, perception, sensors, difference between sensing and perceptions, and etc. But now we are discussing about physical attributes of a sensor. So there is a change in the topic. Your environment is same, but there's a change in the topic in the meet. That's what is a repeatability. Repeatability means it's nothing but like how whenever you are able to sense the same environment again and again, you will obviously not get the same answer again and again, right? So now, before I was discussing about sensing perception, now I'm discussing about attributes. You are in the same environment, but your topic is different, right? So when you are observing the same environment again and again, you will not be you will not have the same output coming, right? That's the repeatability. Deviation from reading to reading. When these are taken for a number of times, when these changes are observed for a number of times, how much deviation you are getting from from first reading, again the second reading you are doing on the same environment. How much is your input? How much is the deviation from the previous one? Third time again you are identifying the changes happening in the environment. Now what is your input? How much is the deviation from the previous input? Like how much accurately your sensor is repeating the same? How much accurately your sensor is able to detect the changes in the environment, even though if you are repeating it again and again. That's the basic property of a sensor. That's the repeatability. Next, resolution. So what is this resolution, guys? So if you take To explain this resolution, suppose if you have a wheel, you're powering the wheel by some external electrical energy, so that, and you're measuring the angular, like how much angle deviation the wheel is like rotating or something in that way. So per unit of electrical energy you're supplying to the wheel, how much angle it is rotating. So in this particular case, per unit of electricity energy that you're supplying to the wheel, how much angle it is rotating. So that's resolution in that particular case. Similarly, per particular amount of period, how much how much amount of changes a sensor is able to sense in its environment. That's resolution of a sensor. So you need to determine field of view, range, responsiveness, accuracy, repeatability, resolution of a sensor. So these are all basic physical attributes which you have to take care when you work with sensors. When you are designing your own sensor or when you are working with any sensors, every sensor will be having all these physical property, physical attributes. And it is advantageous to know about all these physical attributes of different sensors. When you're working on different sensors, whatever the sensor you're working, it is better that you know about all these physical attributes of the sensor with which you are working, so that it will decrease the doubts that you're getting or any problems that you face during you use the sensor, and therefore it will use your it will improve your experience with the sensor even more better. Next, power consumption. Coming to power consumption, right? Power consumption is one hot topic that we all are aware of, right? We need a machine or a robot to work more accurately, like you need more high efficiency from that particular robot or a machine, but the power to be consumed must be less. That's the basic, because why power should be consumed less means more the power it is consuming, more more money you need to invest on power generation. So people need everything more accurate and efficient with less investments. So your robot or your robot or the sensor that you are using in the robot must be it should give you high efficiency, accurate readings, and it should be able to detect every single change happening in its environment. It should be more sensitive to its changes in the environment. It should be accurate. It should be responsive, and then its field of view should be high. Its range should be high, but it should consume less power. So if it consumes less amount of power, thereby you can say that your sensor, it can in other words, you can say that your sensor will take less power, but it will give you more work efficiency. Then it will be advantageous, right? Obviously, it is more advantageous if you are investing less. If you are investing less on power generation, but your sensor is consuming less power, because you need not to generate more power because your sensor is consuming less power, but it is giving you high output, high accurate output, and it is giving you accurate, appropriate reactions to the changes in the environment. Then you can say that your sensor is a very efficient sensor. So power consumption is also a very important attribute to be taken in care when you're designing a sensor or working with the sensors. And this power consumption, guys, it will give you a very high amount of effect when you're working with actual sensors. Sometimes your sensors may be more effective, but because of this high amount of power consumption of these sensors, like your sensor may be more capable of doing high amount of works, but because of this high power consumption, sometimes you need to invest more amount in that. Then like in that way, your power consumption becomes more important in some situations. Then hardware reliability. So a sensor is a hardware device, as we all know. So how much durability are we going to get from this sensor? Like how much durability? What do you mean by durability, guys? Durability in the sense how much period of time we can depend on this without getting any hardware repair or something, hardware failures or something. So how much is the reliability of the sensor? That's the very important thing to be taken care when you're designing a sensor. More you can depend on your sensor. Like if your sensor is able to work for a longer period of time, if you're able to rely on your sensor for larger amount of time without without any failures, then in that case you can say your sensor is highly capable of performing for a long period of time. Its performance is performance measurement is high because it is not getting any failure, even it is working for a longer period of time. So that's what is hardware reliability. How much you can rely on your sensor, that is hardware reliability. So these are the basic physical properties, guys, which you need to keep in mind when you design a sensor, when you're working with sensors. And when you're working with sensors especially, you need to know about it's better to know about all these physical properties. Next, let us see about the classification of sensors. Right, here we have basic classifications like active sensors and then the passive sensors. So what is an active and what is a passive sensor? If you come to an active sensor is a sensor which will do the work of both reading and writing to the environment. So what do you mean by reading and then writing to the environment? So reading and writing means sensing the changes in the environment, and it will like example, yeah, let's go to an example and then you'll understand it more clearly. Let's take a radar or a GPS. So if you take a radar, okay, so it will send the signals, it will emit the signals, and those signals will hit on a surface, and those signals are again reflected back. Those reflected signals are again taken by the reflect like emitter and then the receiver. So that's a case of an active sensor where you are reading and then writing to the environment in both cases. So that's called as an active sensor. Example, GPS, radars and everything. Those are active sensors. And passive sensors means which can only read to the environment. So what do I mean by only reading to the environment? Reading the environment in the sense it can only take, or it can, like these passive sensors, you can tell them as a true observers of the environment. What do I mean by the word true observers? True observers means they will they will not do any changes to the inputs that they take from the environment. So you can see in the picture, a man is running, and whatever the waves that are generated here, far infrared rays, those are emitted, and those emitted rays are identified, are detected by the sensor. That's it. Nothing else is done here. The sensor is detecting the signals coming towards it. That's it. It detects us. It detects the it accepts those waves. That's it. That's passive method or passive sensors. Examples of these are like thermal sensors, electric field sensing, metal detectings, etc. So if you take the thermal sensors as an example, basic example is thermal sensors. You have a thermal sensor. What is the basic use of a thermal sensor? It will detect the temperature around it, right? So it will only detect the temperature, and whatever the temperature is detecting, it will show you on the screen. Or what if there is a screen, it will show you on the screen, or if whatever the output method it has, it will show you the output. Whatever it is sensing, whatever the temperature it is identifying or detecting, that temperature is shown to you, right? No other changes to the input is done, but neither by the sensor or neither by the user. Whatever it is detecting, it is shown. That's the basic example of a passive sensor. So active sensors read and write to the environment, whereas passive sensors will only read the environment, which means they'll detect the changes in the environment, and those changes are exactly shown to you. That's it. Examples like thermal sensors, electric field sensings, metal detectings, and etc. Next, when we discuss about this active and passive sensors, now the topic comes remote sensing, active remote sensing, and passive remote sensing. So what is the basic definition of remote sensing? A remote sensing means without coming into contact with any of the object, you're able to identify the physical characteristics of the object. That is said to be called as remote sensing. Okay, so without coming into the physical contact, even though you are not in physical contact with something, but you're able to identify the physical properties, physical attributes of that particular object, then that is said to be called as remote sensing. A very, very, very well-known example of this remote sensing is like reading the Earth's surface from the satellites. What are the satellites you're seeing in this picture? They are doing remote sensing. It may either be an active or a passive remote sensing. We're going to discuss that, but they are doing remote sensing. Why I'm saying that these satellites are doing remote sensing means because these satellites are neither in direct contact with Earth. They are just in a particular orbit at particular distance from Earth, and then they're rotating in that orbit, and then they are studying the surface of Earth, right? These satellites are those which will give you the geographic maps, geographical images, like where you can identify this land, forest, and etc. These are the things which will give you all those about all the details about the surface of Earth. So without coming into direct contact with the surface of Earth, they are able to identify the changes, identify the structures of the Earth, land, and everything. That's why we say that these are doing remote sensing. So now coming into two types of remote sensing: active remote sensing and passive remote sensing. So what is an active remote sensing means? So in an active remote sensing, whichever the sensor is there in this particular satellite, that particular sensor will emit the radiations, and it will accept those reflected radiations, and thereby it will perceive the data, or in other words, you can say it will process the data and give you the output about the structure of the land or everything. How much of greenery is there in that particular area, how many trees are there, what is the elevation of the tree, what is the land height, what is the sea level, how much above is the land from the sea level, how much below is the land from sea level. All these are identified by these sensors. So all these are identified by these satellites. So if this satellite is having a sensor which is capable of emitting the radiations and then detecting the reflected radiations by itself, that is active remote sensing. But coming to passive remote sensing, here in this passive remote sensing, this satellite is only able to take the input. It is only able to detect the input coming to it, input radiations coming to it, but it is not able to reflect. It is not able to generate its own signals towards the Earth. Now, where are these signals being reflected? They are reflected from the Earth's surface. But where are these reflected radiations coming from? These reflected radiations are coming from the sun. Here, sun is an external source. So, an external source is emitting an energy towards the Earth. Those rays are hitting the surface of Earth, and after hitting, they are reflecting. Those reflected radiations are accepted or taken as an input by the sensors in the satellite, and then they are processed, and then the data, appropriate data, is released out to the scientists. So this is passive sensing. Example for active and passive sensing in daily life, you can take it as, whenever you go to photo shoots, you will have, suppose assume a condition, your friend is having a camera. So whenever your friend clicks a photo of you, there is a flashlight coming from the camera itself. You need not to have an external flashlights to focus on you. The camera is itself having an inbuilt flash. So when he clicks the button, there is a flashlight coming towards you. That flash falls on you, gets reflected back, and depending on that reflected flash, you're getting an image, right? That's an example, basic example, a very, very basic example of active remote sensing. It's not like, it's like an analogy to active remote sensing, guys. I'm using this example to make you clear what is a basic remote sensing idea. It can generate its own radiations, or it can emit its own rays, and it can accept those rays and then can process the data and then give you the output. That is active remote sensing. And passive remote sensing means if you go to some high level studios or something, there you will have only camera. You will be having two separate flash stands which will be focusing the person. Then the photo is taken, which means you are having two external flash stands. In some cases, in some photo studios, still they are using this technology. Like you'll be having separate flash stands, and then those flash stands are focused on the person. Then a photo is taken. Camera is not having any flash. Okay, but to take the photo, you are using two external flash sources which will be focusing on the person. Those lights will be falling on the person. Those lights are reflected back. Those reflected lights are taken by the camera, and then you'll be getting the photo of the person. These are the two different cases. A photo can be taken by a camera, inbuilt flash, or an external flash source. Whenever you have an inbuilt flash in your camera, it is an active remote sensing analogy. Whenever you don't have an inbuilt flash, but you are using external flashes to focus the person to take image, that is a passive analogy to passive remote sensing. That's what happens in this satellite also. So if the satellite is having its own sensor, it can able to emit the radiations and detect the radiation. That's active remote sensing. If it is not having, it is not capable of emitting the radiations, but it is only capable of receiving the radiations and then process the data. That is passive remote sensing. Right. Then you have two more types of sensors: contact sensor and then a non-contact sensor. The name itself. The name itself detects what is the name here itself detects, guys, contact sensor and then a non-contact sensor. So a contact sensor means like your sensor is coming into contact with some physical environment. A non-contact sensor means it is not coming into contact with any physical environment. That's the basic idea. So contact sensors uses transducers for sensing operation. Some mostly used contact sensors are like potentiometers, strain gauge. Your strain gauge you're going to discuss in further slides. Why the strain gauge is called a contact sensor and what is the exact meaning of a contact sensor, you'll be understanding it there. So it requires a physical contact. Yeah, see guys, I told you a contact sensor will come in some physical contact with its external environment. But then you can say that the sensor is a contact sensor. A basic example of a contact sensor is a touch sensor. So if you have a robot, take a robot, you can imagine a robot in your mind. A robot will be having a hand, it will be having fingers. So a robot finger can, it is capable of holding some devices in its hand. So it can sense that it is holding something. Whenever the robot's hands are free, it can sense that it is not having anything in its hand. So how it is able to sense? It's because of touch sensors present in the fingers of the robot. These touch sensors will come into action whenever this robot hand is coming in contact with some physical devices, physical quantities or entities which are in the external world. That's why you say a contact sensor needs a physical contact with the external world. So they are generally used to detect changes in position, velocity, acceleration, force, torque, holding devices, and for all these different purposes, you'll be using these contact sensors. Right. Next, a non-contact sensor. A non-contact sensor requires no physical contact. This is obvious because the name itself suggests non-contact sensor, which means you don't need any particular physical contact with any of the external environment. Just It's a sensor without getting in contact to the external environment. It will be sensing and giving you the output. It is used to detect the existence, distance, features of the objects and etc. A best example for this non-contact sensor, like a proximity sensor you can take, because a proximity sensor, it will not come into basic contact with the humans or something, but proximity sensor will detect in how much distance the object is there. So yeah, coming into proximity sensor, I'll be explaining you what is a proximity sensor. But yeah, such type of examples are good examples for this non-contact sensors, which means you're not coming in physical contact, but you're sensing something, a change happening in the environment. That's a non-contact sensor. A non-contact sensor uses wear-free technology. Sensors contain no friction of moving parts. Obviously, there will be no friction, guys, because it is not coming in contact with any of the external environment. So obviously, there is no friction involved. If there is no friction, there is no wear and tear. Therefore, mechanical failures also will be reduced. These all are like interlinked with each other. That's it. That's basic idea of contact and non-contact sensing. Yeah, resistive sensor. This resistive sensor, how many of you have come, like, remember the basic formula? Resistance is equals to rho L by A, where L is nothing but length and A is nothing but the area of the conductor. That means like R is a resistance, right? So see, the second point states that resistive sensors works on the principle that the conductor length is directly proportional to the resistance of the conductor and is inversely proportional to the area of the conductor. Right, guys, most of the people among us prepared either for NEET or prepared either for JE, right? Saying that in the physics, you'll be having a formula called resistance R is equals to rho into L by A, where L is the length of the conductor and A is the area of the conductor. Yeah, so that basic idea, that basic concept is used in this resistive sensors. Resistive sensors works on the principle that the conductor length is directly proportional to the resistance of the conductor and is inversely proportional to the area of the conductor. This is the basic working principle of a resistive sensor. Now, why is this resistive sensor used? It is an example of a passive sensor which converts a mechanical change such as displacement into an electrical signal that can be monitored after conditioning. So whenever you have a mechanical changes, like whenever you're having a changes in mechanical change sense, you have some physical change in any of the physical entity, they will be changing the resistance of the item. When you are using iron, suppose you have an iron is having some resistance, and if suppose you are changing the length of the length of the iron rod, automatically the resistance of the iron rod also changes. So such changes, mechanical changes such as displacement or changes in the length, changes in the displacement of any object, those can be identified, and those changes can be converted into electrical signals that can be monitored after the conditioning. So that for those particular purposes, you will be using these resistive sensors. Yes, remember this basic principal property of resistive sensors. It works on a principle: conductor length is directly proportional to the resistance, and area of the conductor is directly proportional. Inversely proportional to resistance. So depending on this particular theorem, this particular principle, we are able to identify the mechanical changes such as displacement, changes in the length, and area changes, etc., and able to convert that changes, mechanical changes, into some electrical signals. That is resistive sensors. Now, this is like a basic extra information on sensors, guys. Like, what is sensor modality? Which means it's like sensor which measures some form of energy and process it in similar ways form a sensor modality. Modality refers to the raw input used by the sensors, which means like you have some form of energy and it processes it similar ways to similar way forms, which is like you are having a form of energy, you are having a raw input. That raw input is exactly taken and processed without any modifications. That is said to be called as a sensor modality, which means like like the raw input is directly used for perception. You're not doing any external operations after you take the inputs. See, guys, that's why it's mentioned. Modality refers to the raw input used by the sensors. The raw input, which are the input you're getting from the changes in this environment, you're taking it and you're processing on the raw input. You're not doing any external changes after you take the input. That's nothing but modality. That's sensor modality, where sensors will sense and then take the input, will not do any sort of external additional modifications to the input, but will use the basic raw input taken from the environment to perceive and then cause and then do an appropriate action. So that's nothing but sensor modality. This is an extra information on
Just a
sensors.
second, Tarun.
Yeah.
Yeah, guys, are you able to understand what modality is? Like, which part of the sensor will define this sensor modality? Can you guess? we saw this term on some previous slide. Just try to recall it. Come on, guys, you can unmute or you can just type in.
Guys, come on, involve in the chat, guys. Whether it may be correct, wrong, anything. Your response gives us motivation, guys. Come on, we have so many sessions to forward.
I'm sorry, Avantika, I'm not asking you the analogy. Yeah, Venkatramanan. I'm sorry. Yeah, Venkatraman. You are right. That's transducer. First of all, did you understand like what is a transducer in a sensor? Not only Venkatramana, I'm asking everybody. Avantika, the transducer will help your signals to transform to some other form, which microprocessors or microcontrollers can actually make a meaningful information or meaningful output out of it. So, for example, let us take an analogy of, say, your voice. A robot has to, authenticate you for some bank transaction. Okay, so it is using voice biometrics. So, what do you think when you speak out your name? How does that robot? I mean, it will sense definitely, and for perception it has to send to microprocessor, right, or microcontroller, whatever you are using there. So meanwhile, okay, definitely it is a thing between sensing and perception. The transducer will receive the voice signals which you are speaking. Okay, when you speak, the signals are what, they are in form of waves, am I right? So yeah, correct. Venkatraman is speaking. Correct. It converts one form of signal to another. Let's take this analogy. So when you are speaking out, the signals are in form of waves, right? You all know that sound travels as a wave. It needs a medium to travel, and the medium is air generally. So here in this case, the robot will receive these waveforms on its sensor or whichever audio sensor it is. And this particular sensor will contain a transducer which will convert these wave signals into such readable data by microprocessor or microcontroller. Fine, so that is a transducer, and the sensor modality you were seeing just now, that is defined by this transducer only. I hope that has cleared what sensor modality is, because it refers to the raw input which you take in. So the raw input is going to directly to the transducer, right? So the manufacturer of transducer will be defining this modality. Is that clear? Guys, I need response, or you can give a thumbs up. All right. So if you have any doubts, you can unmute and speak up, or else you can type in chat. Okay, Tarun, you can continue.
Yeah. So we are quickly moving into different types of sensors, guys. Now we'll be discussing about proximity sensor, and then you have Hall effect sensor, and we'll even be discussing about temperature sensors. We have few different types of temperature sensors, and then you have distance sensors as well coming up. So we'll be discussing about all these encoders, dead reckoning, and all these topics as of now. So right, coming to proximity sensor, we heard this topic even like I used this word proximity sensor even earlier as well. Yeah, coming to this proximity sensor, what is the basic use of this proximity sensor is you can see this proximity sensor coming into action when you go to shopping malls, guys. Whenever you go to a shopping mall, as you will be seeing even in some movies, even though if you have not experienced it physically as of now, even you are well aware of in some movies, like whenever a person comes near to a door will automatically open itself, right? So that's a basic example of a proximity sensor application, guys, where whenever a person is if he enters into some range where the sensor can detect that there is some object near it, it will take an appropriate action. So here in this case, whenever a person approaches the door, the sensor will detect that someone is coming towards it, and thereby it will open. The action is like it will open the door. Thereby the person will pass through the door and then he'll enter into the room. So this is a basic application. So this is a very basic and well-known, well-experienced application of using proximity sensors. So that's the basic use of proximity sensor. See here, you're having a target. If you observe the diagram here, you have a proximity sensor, and then you have a target. The target is like 1 mm, and it is at some calculative distance from the sensor. So whenever it is at a calculative distance, it will detect that some object is there in this particular range, and therefore it will take some appropriate actions. That's the proximity sensor. So coming to the theory part, measure relative distances between sensor and object in the environment, guys. So that's what, as we are speaking till now, relative distance between sensor and object without coming into contact with the object around it. When it comes to its particular range, it will identify that some object is there around its environment, and thereby it will take some appropriate action. So that is proximity sensors job. So most proximity sensors are active in the sense they will emit. Like if it has to detect something is coming towards it, it has to emit something towards the object, and it emits something towards it. The rays will hit the object and it will get reflected back. When it reflects back, the proximity sensor will identify those reflected rays, and thereby it will judge the distance between, like depending upon the reflecting time, distance, velocity. The proximity sensor will it will identify, it will calculate the distance of the object from the sensor, and if it is within its range, it will open the door. As in case of our shopping mall example. So that's what happening in the fourth point. These sensors make use of signals to emit and receive the same signal after it is getting reflected due to presence of object. So when it will emit a signal, and whenever there is an object present in the signal's way, those signals are getting reflected back because of the presence of object in its way, and with the help of distance, like in how much of time the rays are getting reflected back, and how much distance how much of speed, like velocity in the sense it's like 310 to the power 8 meters per second, right? The velocity of each and every light in its earth atmosphere is 310 to the power 8 meters per second, or throughout the universe. So with the help of time taken to travel back after reflecting from the object, and the velocity, using this distance velocity time relation, you can calculate how much distance the object is away from the sensor, and if that distance calculated is within its range, it will take the appropriate action. In case of our shopping mall example, if it is within its range, it will open the door, so that the person can without getting hit to the door, he can automatically, without even opening the door by himself, the doors will get automatically open. It will be open for him to pass into the room. So that's the basic working principle and working of a proximity sensor. So many proximity sensors such as sonar, IR, ultrasonic, and all these are examples of different proximity sensors, right? So next we have proprioceptive sensors, and then dead reckoning. So before we discuss about the proprioceptive sensors, we have to discuss about dead reckoning. What is this dead reckoning? Dead reckoning means you will be estimating the future position of your robot or whatever the bot you have, basing upon your present positions and your past positions, guys. That's the basic idea in this topic. So yeah, you can see that it is a process of estimating one's current position based upon previously determined position, and advancing that position based upon speed, elapsed time, and then course. So what do you mean by advancing that position? Which means you're calculating, you're taking the present position, and then with the help of its previous position data, and with the help of its speed, elapsed time, course, and everything, you will you'll try to judge in this coming period of time where it is going to reach, like in the future time where this particular robot is going to be there. Suppose it has started near my house door at particular moment of time, and after 1 second it has reached to the bedroom, and I can calculate the distance from the entry door to the bedroom door, and then how much of time it has taken, and with the help of that I can I can estimate in the coming period of time, in coming 1 second, 2 seconds, or some milliseconds or something, where this robot is going to be found. So that's the thing. That's the main idea behind this dead reckoning. So many proprioceptive sensors are such encoders, GPS, global positioning systems, etc. are all these particular example, guys. And these proprioceptive sensors work on this dead reckoning concept only. So GPS also, it can be taken as an example of working on this dead reckoning process. And next you have encoders. Yeah. When you speak about encoders, you have to speak about optical encoders. So before I speak about optical encoders, I have to speak what is an encoder. So it is used to measure the turning distance of motors. What do I mean by turning distance? Here in the picture, we can clearly see that there is some device which is counting the number of spokes passing by this particular tip, and then it will count the number of spokes on a particular wheel. The same way, encoders are used to calculate the turning distance of motors, like how much distance the motor is turning in the given particular period of time. So that particular distance, how much distance the motor will be turning in terms of rotations, you can say how many rotations the motor is turning in the particular period of time. Those will be identified by the help of these encoders. So what do I mean? So before I told that when you speak about encoders, you need to speak about optical encoder. So the basic idea of optical encoder, guys, optical encoder means you will be having a wheel rotating. A basic scenario means you'll be having a wheel rotating, and over a wheel you're having some small holes, continuous small holes, which are at a equal distance from each other throughout the wheel. And you'll be placing a wheel. You'll be having a wheel, and in the two opposite sides of the wheel, you'll be having a emitter, like a light source emitter, and then you'll be having a receiver. A light source will be emitting the light. And whenever the wheel, I told you that you are having some holes on the wheel. Throughout the wheel, you are having holes, right? So when the light passes through those holes, it will be received by the receiver. So the count, it's one hole. Then second, it will pass to the second hole again. After another further rotation, second hole will come in the position. Light will pass to the second hole. Then it will be received by the receiver. You can say that there are 2 holes, then 3 holes, 4 holes. Like that, you can say how many holes are there. So depending upon the number of holes it covered, you can say how much angle or how much distance the motor has turned. That is nothing but optical encoder. So why this name optical encoder means you are using this optical devices like emitter and then receiver. Light is getting emitted, and number of times the light is detected by the receiver. Those depending upon those number of times it is detecting the light emitted and then received. With the help of that count, you can say how much distance it is rotating or how many rotations the wheel has rotated. So that's the basic idea of encoder and then optical encoder. There are different encoders, guys. You have magnetic encoder, mechanical encoder, resistive encoder, and an optical encoder is also a part of encoders, like encoder technology. But a very important and a basic, mostly used in the industries, is optical encoder. That's why I just wanted to discuss about the optical encoders as we came to this topic, right? The next topic is Hall effect sensors. So the name itself suggests an Hall effect sensor is used to detect the Hall effect. So what do I mean by Hall effect means? Here in the diagram, you can see clearly that you are having, you're having a conductor plate, and that conductor plate is, it is connected to an electrical source. So like electrical energy is passing from one end to another end. But when you are bringing a magnet near to that particular conductor, when there is no magnet, imagine there is no magnet, guys. Only there is a conductor, and that conductor is connected to an electrical source among its edges, like this left edge and right edge. So this left edge and right edge are connected through an electrical source, and thereby electrons are passing from the wire conductor. They are like completely rotating inside the wire and the conductor. So it will be a straight path. But when you bring a magnet in between, when you interfere a magnet in between, this inside the conductor, when there is no magnet, the direction, it is a straight line. The electrons will be traveling in a straight line. But when you bring a magnet near to the conductor, these electrons, these are divided into positive charges, like what are the charges are rotating in this wire. They will be divided into positive and negative to one end and the other end. They will be separated, positive charges to one end, negative charges to the another end. So when you have this positive and negative charges, initially every charge is rotating inside from the conductor to the wire in a straight path over the conductor. But when you're bringing this this magnet near the conductor, these positive charges are going to one end, and then the negative charges are going to the other end. That's why you can see this gap. There is a gap. Positive charges, like this red colors are one type of charges, and this blue color are different types of charges. They are towards two different opposite ends. So whenever you have different voltages on two different ends, you can like whenever you have this charge differences on two different ends, you can actually measure the voltage difference also. So that is basically the Hall effect, and with the help of this Hall effect sensor, you can detect an Hall effect going on in the particular environment. So the name itself suggests that it is a Hall effect sensor, means it is used to detect the Hall effect. So these sensors uses the magnetic field to detect the proximity speed displacement of any mechanical system. So with the help of this, these Hall effect sensors, they'll use this magnetic field, interfere of the magnetic field. Where you're using this magnetic field in this particular example, in this particular picture, you're bringing a magnet. This magnet will cause the charges to go into two opposite directions. So when like opposite directions in the sense, one set of charges will be on one direction, other set of charges will be on the other direction, like positive charges towards one end and negative charges towards the other end. So you can measure a voltage, you can measure thereby a voltage difference. Thereby, these sensors are non-contact sensors. You're not bringing this Hall effect sensor in contact with the semiconductor, or neither you are bringing them in contact with the voltage calculator, or you are neither bringing this Hall effect sensor in contact with the magnet or nothing. These are non-contact sensors, which means these sensors need not come into contact with any of this particular. It need not to come into contact with wire. It need not to come in contact with the conductor. It need not come into contact with anything. It is a non-contact sensor, and it will basically, with the help of the magnetic field, based on the Hall effect principle, it will detect the proximity speed displacement of any mechanical system, right? So yeah, in this picture towards the right, you have a wheel rotating, and then you have a device, right? This device is nothing but Hall effect sensor. So in this Hall effect sensor, this yellow part which you are seeing in this particular device, to the left of the wheel, that is a Hall effect sensor, and then you are having a magnet. So it is not in contact with the wheel, but it can count the number of rotations of the wheel, and it can make the wheel to rotate, and everything it can be doing with without coming into contact with the wheel. It can make the wheel to work, and it will detect the displacement of the wheel, how many rotations it is doing, or the proximity speed and everything. This is what a Hall effect sensor is. It is a non-contact sensor. Without coming into contact with the wheel or without coming into contact with any physical entity, it will detect the displacement, speed, and etc. Why it is based? How it is detecting? It is detecting with the help of Hall effect, bringing in some magnet near to an close to electric circuit. You will get a potential difference, and with the measure of that particular potential difference, you can measure the displacement and then the speed of the mechanical system. Next. This is working principle of Hall effect, guys. So initially current is applied to a thin metal strip. You have this thin metal strip, or you can say you have this conductor. So in presence of it is initially current is applied to that strip, and as we have discussed as of now, presence of magnetic field perpendicular to the direction. Like you are bringing the magnet in a perpendicular direction to the conductor. So you bring a magnet in perpendicular direction to the conductor. In the perpendicular direction, the charge carriers are deflected with a Lorentz force. So when you have a closed conductor, when you have a closed electrical circuit and you have a conductor in it, you're bringing a magnet perpendicular to the direction of the conductor. Then according to the Lorentz effect, the charges are deflected towards the opposite sides. So based on the Lorentz force, because of the generation of Lorentz force, charges respective charges are divided into two different opposite ends, and therefore in turn produces a difference in electrical potential between the two sides of the strip. this potential can be, it can be calculated. Since the opposite charges are on the opposite directions, this voltage difference can be calculated, and thereby with the help of this voltage difference, you can detect the speed displacement of the mechanical systems. So this is the basic working principle of the Hall effect. Next, strain gauge and working principle. So by hearing the word strain, what is the basic definition, basic idea of strain? Strain means it is nothing but how much deflection and how much deviation you are getting in any physical entity. That is strain. So that's strain gauge is a device which is used to measure the how much strain you are applying on any object. So that is nothing but a strain gauge. So how the strain gauge usually works means you have these two electrical wires, leads. You call them as leads or leads something. So when you connect these, like with the help of this Wheatstone bridge, we'll be connecting this Wheatstone bridge to a voltage source, and you have this R1, R2, R3, and R4, right, guys? We recently you people have recently completed this Wheatstone bridge in your intermediate as well, or in your 12th and 11th. So in this Wheatstone bridge, you have R1, R2, R3, and in place of R4, you're connecting this strain gauge. How you're connecting this strain gauge? With the help of these two electrical wire leads that you are able to see here. With the help of these two leads, you're coming and connecting to the strain gauge. Okay, sorry. This strain gauge, with the help of these two electrical leads, you're connecting to the Wheatstone bridge. So whenever there is a strain, like when you're having a resistive foil over this strain gauge, whenever there is a strain applied on this particular foil, there is a deflection in this particular foil. That means change in length, you can say, or change in area, you can say, whatever it may be. So we know R is equals to rho L by A initially. Before only we have discussed resistive sensors, where we discussed the formula R is equals to rho L by A, where resistance is directly proportional to length and inversely proportional to area. So when there is a change in length or area, which means you're applying a strain. When you apply a strain, there is a change in length or area. When there is a change in length or area, there is automatically a change in resistance as well. When there is a change in resistance, there is a voltage difference generated, and with the help of this voltage difference, you can relate the voltage difference that you have identified with the amount of strain. That is called as gauge factor. So this gauge factor, it will relate the identified or measured voltage difference, voltage change with the help of this gauge factor and this voltage identified. You can identify how much amount of strain is applied and how much amount of strain is applied on the object and how much it is getting strained. So that is a basic working principle of a strain gauge. See, coming into theory part, this is a device used to measure a strain on an object. So the help of the strain gauge, you can identify the strain applied on the object. So what is working principle? An object is initially attached to a strain gauge. Whenever an object gets deformed, it will cause for resistance change. Why a resistance is changing? Because there is a resistive foil. So when the strain is applied on the object, the resistive foil will get deformed, which means deformation of resistive foil means it may either get changed in its length, area, etc. And change in length or change in area will automatically change the resistance. So there is a change in resistance. This resistance change is related to the strain by using a gauge factor. So with the help of this gauge factor, you can identify the resistive change. You can identify how much of strain is actually applied on the object. Right. Next is LiDAR sensor. So LiDAR stands for light detection and ranging. So this is a very well-known, it's a well-known sensor obviously we know it very well because it's a technique to determine the distance from an object and the target by emitting a laser towards the surface. Yeah, in the GIF itself, you can see there is an emitter, there is a receiver. Emitter emits this, light rays towards the object, and when the emitter emits the light rays towards the object, the light rays reflects from the surface of the object. They are getting reflected back, and those are received by the receiver present in this particular LiDAR sensor, right? So this is nothing but the basic working principle of this LiDAR sensor. So where you can use this LiDAR sensor, you can relate this working of LiDAR sensors with an analogy of sonars, wherein they are used in ships. Sonars, right, guys? Sonars basically used in ships to identify how much distance the seabed is from the surface of the ocean. So you can relate this working of LiDAR sensors also with that particular sonar sensors, LiDAR sensors. All this works on the same principle, like emitting a source of energy and receiving the reflected energy, rays. And with the help of this reflected rays, you can identify the distance. So the basic question arises here is how you are identifying the distance of object by this emitting and receiving. So how much distance is traveling, how you need to identify the distance between the lidar sensor and then the object. To do that, you will identify how much of time the light ray is taking, after emitting and to get reflected back, right? The time you'll calculate, and then the speed is nothing but 3 into 10 to the power 8 meters per second, which is constant, light speed constant throughout the universe. So you have speed of light, which is 3 into 10 to the power 8 meters per second, and then you have the time taken, like you will calculate the time taken for the light ray to emit, to after emitting, you will keep track of the time, after how much of time that particular ray is getting reflected back, and how much of time the lidar is able to receive that particular reflected light. That time difference, and then the speed with the use of this distance speed time relation, v is equal to s by t, where speed is equals to distance by time. So distance is equals to speed into time. With the help of this distance, speed, and then time relation, you can calculate the distance, right? So 3 into 10 to the power 8 meters per second into the time taken for reflecting back. So that you can get the distance of the object from the lidar sensor, right? Next, where you can use this lidar sensors, you can use this lidar sensors in deriving the high resolution elevation data. Elevation data in the sense how much of height above hills are there from the surface, like elevation data, and then canopy heights. You have different canopies, like hills, mountains, etc., etc. So to identify those heights, and reflected back by the 5 feet height ray. Again, they'll go penetrate inside. Some rays will penetrate inside. There again, they'll be reflected back by the 2 feet height ray. Again, these some part of rays are reflected. Some are again penetrating inside. There you have a bush, and that bush will bush or grass, whatever it may be, that again will reflect back the rays finally back to the sensor. Again, you have the land. That land also, like the surface of the forest, it will reflect back the right ray. So here, finally, 5 times the lights are reflected. The same ray emitted, but 5 different like 5 different objects are reflecting the same light ray, which means one below the other, one below the other, one below the other. The structure, like in that way, you can estimate the structure. Like there is so here you are receiving 5 different times, which means the light is passing through 5 different objects in the same particular environment. In that way, you can identify the structures of forests. Next, to provide a 3D view when you're driving inside the cars. So probably in future, you can expect these cars using this lidar technology as soon as possible. So they'll emit the radiations. Like you'll be like you can even Google it, or you can even go to YouTube. There are already some videos on this cars working with lidar sensor, guys. You can go to YouTube and search. You'll be having one cup-like structure present over the car. That is nothing but a lidar sensor. It will be emitting the radiations. Those emitting radiations are reflected back by any device surrounding in its environment, and after getting it'll get the reflected rays, and it'll calculate in how much distance that particular car is away from me, how much distance a particular woman is away from me, how much distance I can find a tree in front of me. So how much distance is there a turn around me? Is there a turn coming up? So in all these applications, it can be used. These are uses of lidar sensor. Next, you have temperature sensors. Yeah, guys, what is a temperature sensor? A temperature sensor, by the name itself, you can identify, or by the name itself, you can understand that a temperature sensor will detect the temperature. It is used to detect the temperature of the environment, and it will convert the input data into some electronic signals or something. That's obvious, because whatever the inputs you're taking, you need to process the inputs and then convert into some usable data to give you some appropriate reaction. So keeping aside converting of input data to electronic data and everything, keeping it aside, the basic work of a temperature sensor is to detect the environment temperature. It's to detect the environment temperature around it. So some temperature sensors may be, they may be required to come in direct contact, and some may be required to come in, some may be, non-contact temperature sensors as well. So it's like obvious that there may be temperature sensors, like contact temperature sensors and non-contact temperature sensors. And contact temperature sensors means they need to come in contact with the physical environment, to the physical entity, to measure the temperature of the object. And non-contact sensors are those which are need not to come in contact, so the which are not mandatory to not mandatory to come in contact with the physical entity to measure the temperature. So that's the basic difference. And a very well-known example of a non-contact sensor is an IR sensor. So basically, IR sensors are well-known examples of non-contact because they will not come in direct contact with the environment, but instead they measure the temperatures. So here in the picture, you can see 4 different types of temperature sensors, guys. RTD, which means like resistance temperature detector, and then thermocouple, thermistor, and then you have a semiconductor. So we'll be speaking about the RTD first. RTD stands for resistance and then temperature detector. So it's a device in which the resistance will vary with the temperature around its surroundings. So it will be continuously detecting the temperature in its surroundings, and with the help of this detected temperature in the surroundings, its resistance will be continuously varying. So in that way, this RTD will be usually working. So to detect the temperature in its surroundings, to detect the temperature changes in surroundings, its resistance will be continuously changing. It needs an external electrical current which will be applied, which causes a change in the voltage. So this RTD will be connected to some external electrical current source. That external electrical current source will bring some voltage difference that will thereby result in some resistance change. So in this way, with the help of this voltage difference generated and then the resistance changed, by this voltage difference generated is a very good entity to identify the temperature change, and even this resistance change with the help of this voltage and resistance changes happening in the external because of this external current that you have supplied to this device, you can identify the temperature change as well in the environment. So that's the basic working principle of the RTD. Next, moving on to the thermistors. Thermistors, these thermistors, they are temperature dependent resistors. Simply, you can say this thermistors are temperature dependent resistors. There's more to say about thermistors in the sense they'll be used as similar to RTD thermocouples in semiconductors itself, as they are low current. They are lower current protections. For lower current protections and everything, you can use these thermistors, and they are temperature dependent. You can simply say they are temperature dependent resistance for low current detections and everything. Low current, like when you have a low current, you have a less temperature detections. So in all particular cases, you will be using these thermistors, guys. And then you have thermocouples. Thermocouples. Thermocouples means they'll contain some specific wires which are joined together. This thermocouples, inside this thermocouple, you'll be having some joint where you have two different wires are joined into one junction. So to this particular junction, you'll be applying providing some temperature. So when you apply some temperature to this particular junction, on the other side of the junction, on the opposite side of the junction, some millivolts of voltage will be generated. When this millivolts of energy signals are generated, so this millivolts of signals generated will help you in thereby you can relate this millivolts signal generated with the temperature change that you can observe in the environment. So in this way, the thermocouples will work. So basic working principle of thermocouples means you will be having a couple, like you'll be having a join, or you can say it as a junction. So to this junction, you'll be applying the temperature change or the heat change, like heat or temperature change or whatever it may be. So when this junction is applied to some temperature change, you'll be it will be reflected directly to some millivolts signals developed on the opposite side of the joint. So this millivolts of signal generated, with the help of this signal generated, you can identify the temperature change, which like how much of amount of temperature is changed or applied at the particular joint, you can identify. Next, you have this semiconductor temperature sensors. So the word itself indicates, guys, it's a semiconductor sensor. Semiconductor temperature sensor means basic working principle of the semiconducting sensor means, I'll discuss about the basic working principle. So basic working principle is like junction voltage across any PN junction, like any PN, like the junction, you have a PN diodes, right? A PN diode, you'll be having a junction. So that particular junction, voltage difference across that particular junction is directly, it's a function of variation of temperature. So basing on this particular principle, so you have PN junctions, right? So this PN junctions will automatically have some voltage differences and everything. So at this particular junction, whatever the voltage difference is there, that voltage difference is a function of temperature. So depending on that particular principle, this semiconductor the temperature sensors are usually used. And the basic advantage of having the semiconductor, these are mostly nowadays like semiconductors, transistors are those which are in high usage nowadays, guys. So this semiconductor temperature sensor is also highly used in the industry nowadays because of its small size, low cost, and more efficiency. It works on PN junctions also because of it works on transistors as well. So based on its principle on transistors, PN junctions, and everything, it is mostly used nowadays in the industry. Then finally, you have displacement sensors. Before you close the topic today, you have displacement sensors. So a displacement sensor is like the word itself tells, it's a displacement sensor which is useful, generally used to measure the distances and heights. Like what do you mean by distance and heights in the sense like how much distance distance and height means like you can take a daily life example, like how much distance so and so object is from the sensor, or how much height a particular elevation or a particular building is from the sensor from some particular level. You can usually detect all these small height displacements, like height displacement, etc., with the use of this displacement sensors. So these sensors are highly useful in displacement or position applications such as XY positionings and machinery dynamics and etc. So you can see this displacement sensors mostly used in machinery dynamics and etc. because we have different devices used in the machinery machines, right? In the machinery dynamics, you have lots of devices coming into action. So their positions keeps continuously changing. Like they should be in some XY coordinate, they will be changing to some X plus Y minus X coordinate after some particular moment of time. So where they will be changing, what position they will be changing, and all these minute displacements of these devices inside this machinery parts and everything, these can be used identified by this displacement sensors. So physical characteristics near the sensors like temperature, magnetic fields, etc. None of these characteristics, guys, magnetic field, temperature, nothing will affect this reading of the displacement sensor, because it is here it is mentioned that not influence the displacement sensors. So these magnetic fields, external temperatures, the increasing of temperature, decreasing temperature, presence or non-presence of magnetic field, nothing will cause any change in reading of the displacement sensor. It's an independent of all these changes in its environment. It is used to basically identify these minute changes happening in the XY positions and etc. So yeah, that's it, guys. So that's what is the topic of today. I hope I didn't bore you guys today. And yeah, that's it. Dheeraj, up to you.
Yeah, thank you. So guys, please fill up the feedback form posted in the chat, and also we would like to hear from you